This is the Amp Hour Podcast, released January 20th, 2019. Episode 426. An interview with Dean Pick. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
And I'm Dean Pick of By Performance Development.
Welcome, Dean. How you doing?
Doing well, thanks. Yourself?
I'm good. This is a nice follow-up to our robotics episode last week with Chris Osterwood. We're going to be talking a little bit about actuators, but more than that too, kind of motion and I mentioned mechatronics last week, and so that's kind of what you do. It seems like your consulting work and the companies that you're working on. It seems like you're combining kind of electrical and mechanical. Could you tell us a little bit about that?
Definitely. So we are running a company called Kinetix Automation that is pioneering a new type of mechatronics actuator or a driver that uses shape memory alloy that basically acts in a straight line or linear motion, but can generate pretty amazing force and precision. And there's a pretty detailed or rich history behind that I can get into.
Yeah, that's great. I mean, maybe even before that, could you tell us kind of the state of linear actuation in the first place, like where the industry is right now and how most people do it?
There's a lot of classic technologies out there that a lot of people will be familiar with. It started, I'll say, with hydraulics and pneumatics or air driven parts that go back 100 or even hundreds of years. And then with the advent of electronics and electronic drivers such as solenoids and AC and DC motors, you start to see sort of electrified direct driving. And more recently, we're seeing an emergence of things like voice coils and piezoelectric actuators, which really start to round out the sort of capabilities in terms of how much force or how much movement or travel you could get out of these different products. So they all kind of fall into their own special niche categories.
And the voice coils and piezoelectric, how does that actually work then? Like, is it you're basically just sending electrical signal and it's driving a speaker, like a speaker type thing, and it's
the voice coils are exactly that. If you were to deconstruct a speaker and let's say take the cone off, you could connect that to basically anything, typically low force, but it's highly responsive, obviously, because it's got to react to the sound frequency range. So it's quite good at fast motion, precise motion, but low force. Whereas the piezos are very good at high forces up to a very, very small range. So fractions of a millimeter or thousandths of an inch.
Okay, and that's different ranges for different applications. That's kind of the idea.
Well, the applications, it's you can look at it from one of two ways. If you're looking at an application with a specific set of requirements or specs, you're going to ultimately end up in a certain group of products that are going to be able to cater to that need. Whereas if you started from the actuator and built it forward, you'd end up inside its own capabilities without, and wouldn't really be able to go too far beyond that.
And the other one I've thought about, or not thought about, but I think I've seen before, is it's an actual motor that then just gets translated. The motion gets translated from rotational to linear. Does that have a name, or is that just a general actuator, or is that not even that?
Yeah, you're right. That's actually a whole class of actuators that I didn't touch on. And they're quite popular. So electric screw or electric ball screw are some pretty common names for those. And they're exactly as you say, rotary motor, usually DC or AC driven. And then there's usually some kind of a mechanism that will take that rotary action and turn it into a linear motion. So if you think of like turning a bolt with a motor, the nut that's riding along that bolt could be attached to anything and you would get linear motion from that.
Yeah, I kind of think about the steppers that you see on a lot of low-cost 3D printers, the rotational motion, it's got a lead screw or it's got a ball screw, and then that basically makes makes the gantry move in whatever direction you want it to move. That's where I've seen a lot of it, but that's where I've seen it in my house at least.
Oh yeah, totally. And they're very cheap because they tend not to need closed loop control. You just count the steps, and you tend to get pretty good precision out of those as long as you're not trying to move anything too heavy.
And that kind of brings us to the too heavy kind of. It seems like the stuff that you're working on is somewhere in this sweet spot. And I was looking at a chart that you have on the kineticsautomation.com page, and it seems like you actually map this out of displacement and force. So first off, what is it? And then how does it actually hit into this sweet spot?
Right. So shape memory alloys are a metal alloy of at least two types of metal. And the ones that we've been working with primarily are based on nickel and titanium, roughly equal parts of both. And it was discovered several decades ago that with the right kind of heat treatment and let's say mechanical working, that this material would change shape when it undergoes temperature change. So similar to how water turns to ice, a state change, but in this case it stays solid and the shape of it changes. So in our case, we've really focused on applying the wire product or form factor from this material, which basically goes from a long length to a short length when we apply electricity to it.
And it's because you're dumping heat. Basically, you're just burning heat in like a coil or something. How are you actually using that electricity in this case?
Right. So for us, it acts like a resistive element. A good analogy would be like the resistor wire inside of a baseboard heater. So when you're connecting that wire across a voltage potential, its own resistance, follows Ohm's law. Current flows, and that current is turned into heat inside the wire in a process called Joule heating.
That's interesting. I mean, and so that seems like does not seem very energy efficient. Is that fair to say?
It really depends on the use case for it. For things where you need to, let's say, position something like an antenna or an airplane flap, this is probably the most efficient technology to do that, because once you bring it to a position, it takes basically negligible amounts of energy to hold it. And then on the flip side,
interesting.
Yeah. But on this flip side of the coin, if you need to, let's say, move that flap up and down repeatedly and quickly, let's say a lot of cycling, then it has to go through this temperature change, and you start to lose some of those efficiencies.
Yeah, and so it's almost sounds like a hysteresis kind of effect, where it's like you set it and it kind of stays in this, and then it requires an additional amount of energy in the other direction to make it go back. Is that a good characterization of it?
There is definitely a hysteresis component to it for sure. Yeah, I like to think of it almost like a lattice, which is what the material creates. It's like a crystal lattice, and you could play with like a Mechatronics or I forget the name of that childhood toy set, with the wheels and the spindles. But
K'NEX or Tinker Toys.
Tinker Toys, yeah, that's it. So, by metering the power in, or the electric amps in, you're essentially able to precisely control that Tinker Toy lattice. And what we found is you can control it to a remarkable degree, almost on a nanometer scale, which is
wow,
kind of difficult to describe, in terms of what you could compare that against.
Yeah. And so can you maybe paint a picture too of like how the motion translates? Because I can imagine gating current at the input, right? So you put in 500 milliamps. When you get to 501 milliamps, it moves another, nanometer or whatever you said it was going to be, the actual motion stuff. But like, how does the actual motion translate then, though? So you say you add that extra milliamp. Where does it actually go? Is it inflating like a balloon? Is it like, I don't know, heating like a sandwich?
Yeah, right. So that's a great question. Maybe I'll start by saying what it definitely is not, and that's a pretty common misconception. Is people think of it as a solenoid or a motor where that current is related to the power output. So, I put in, let's say, an amp of power, and I expect to get, 1 foot-pounds of torque or 100 newtons of thrust. Shape memory alloys break that convention. So to answer your question, you put in a milliamp or 500 milliamps of energy, and what that's doing is it's doing one of two things. It's either maintaining that material in its equilibrium, so holding it at its temperature, or some of that is actually going towards changing that lattice, that crystal lattice, which takes some energy in itself. So if you're trying to hold something in place, you're basically just maintaining its heat loss to the environment. But if you're also trying to get some work out of it, then it's a combination of those two things.
Interesting. Okay. And so it is more correlated to temperature, you're saying, than it is to the current that's actually put in there.
That's correct. Yes.
That's I think some of the problem here is that I just don't, I mean, like, I took a material science class in college, but that's, I mean, sure as heck didn't go over this stuff. So then the controller that you make is basically a temperature controller at that point.
We don't actually sense temperature. It's really hard to do, and we certainly tried connecting certain things like thermocouples, but we quickly burnt those up because, well, they conduct electricity. So what we found was there's a very nice correlation between the length of the wire and its temperature. So we can actually infer its temp. Really, what our controller does is act like an interface between a power source, a larger control system, and then our actuator products.
Oh, that's great. That's great. So then, like, you said there's a wire kind of going through this shape alloy. Is it in, like, I still don't quite understand what it looks like though. Like, is it like a pile of silly putty that then expands, or is it like a wedge that kind of slides across two different materials slide across one another? Like, what does the actual internals look like if I cracked one open?
The wire, the shape memory alloy wire itself, probably would look like something like a solid core wire that you'd use in electronics. So if you stripped off the insulation, you would have something that just looks like bare, boring wire. But if you held those two wires,
I've already actually redone my mental picture here. Sorry about that. So the wire itself is changing shape. I was thinking that this was a wire that was imparting heat into like a block of metal, but you're saying that the wire itself is actually the thing so you heat up the wire and the wire does the work. Is that right?
That's exactly right.
Oh, how can a wire actually impart that much force though?
That's a great question. So this wire is not like soft copper. It's got a really, really high proof strength, and it's able to self-generate. And we've actually tested this. It's able to generate enough force to break itself, which is pretty amazing.
That's awesome. Yeah. Okay. That sounds like a really good joke to play on the intern on the first day. Be like, yeah, I go, dump 3 watts through this thing, and then like just have it like bust in half and look at their face as they come back.
Sadly, that's not in the future. That's happened before.
Oh, okay. So like, is it like the wire is kind of in a J shape and then it expands out? Is that kind of how, like, then, so, okay. So now that I've imagined this wire, I'm looking at my finger actually and watching it kind of like bend. And is it like, as the wire heats up, the finger kind of extends to a full length, and that's what actually makes a linear motion happen?
So, not exactly. If you kind of look down at your hands and imagine you got a piece of wire, if you got something lying around, pick it up. So you got this wire between your two fingers and it's in a straight line. If you were to pass that wire over a candle, for example, it would pull your two fingers together. So the wire itself changes length.
Oh, you're saying that I'm holding the wire on either end with 2 fingers on each end.
Yes. Yeah.
Okay. Oh, interesting. So it's actually, the crystal alignment is actually in that, I'm going to call it the X direction. Obviously, it's very arbitrary here, but you're saying that there's a normal length, and then when you heat it up, it shrinks, and that's what actually imparts the motion. And then when you go the other direction, it grows again.
That's right.
Huh. Wow. So how do you get it to actually do it in that line? Like, it almost sounds like a. It's not really a tendon because a tendon actually pulls, right? Like there's actually motion that translates, but this is actually just like a. I don't know. It's like a string that just shrinks up into itself. It's almost like a scrunchie or something like that.
A tendon's not a bad analogy for it. Yeah, and to try to give it some context in the electrical world, we talked about putting that wire across a flame. Well, you could also hook up both ends to, let's say, a 9-volt battery. At your two thumb and fingertips, and that same effect would happen. It would draw your two hands together.
That's crazy. So then how does it translate? So is it like the longer the piece of wire, the less strength it has, or like what are some of the constraints that you actually have to play with then?
Yeah, for us, our first application, which led to the creation of the company, was we needed more force than one single wire could generate. So when we need a certain amount of force, we have to multiply the number of wires, and they all work in parallel. And then to get a certain amount of travel, it's all about how long the wire is. So generally speaking, those wires can work, let's say if it's a 10 centimeter or 10-inch length of wire, I'll go with 100. It's a little easier for the numbers. If it's 100 millimeters or 100 inches, it can shrink between 3 and 8 millimeters or 3 to 8 inches of its total length.
Interesting. So does that mean that you're not going to be a super compact overall unit size because you only get the 3 to 8% of the overall length, but you get the other benefits of holding strength and everything else?
Yeah. So, in terms of its aspect ratio, it can have a very small cross section because the wires have so much strength to them. You can generate a lot of force with not much cross section, but in order to do something of, any real value, you tend to have a long actuator.
So I guess that ultimately plays into what industries are going to be interested in this kind of thing, right?
Right. Well, I guess the industry that we spun it out of was an automotive application where we were controlling a motorcycle clutch. But when we spun it off into kinetics and started, talking with different industries, we saw that there was all kinds of applications that we hadn't really thought about in aerospace, in robotics, for grippers, for clamping or workpiece holding, and a whole just variety of very interesting applications.
Yeah, I would think the thing that I think about is like the holding force that you need. Is that the right term?
It's when I talk about the precision, really depends what your feedback is. So you could have really precise positioning, but you could also have very precise holding in terms of how much you're clamping on something.
Right. So like if you're like a robotic finger, you don't want to crush the egg that you're holding or something like that because of noise or whatever else.
Right. Exactly. It could hold an egg, or if that egg was 2,000 tons, it could hold that too without marring the surface.
Yeah. Yeah, because and then you're also saying that the amount of power that it takes to hold is also much less. Because that's one of the things I had never thought about before I started looking into this stuff was, you say you spin up you have a what did you call it? Like a ball screw linear actuator type thing. You spin it and you spin it and you spin it and you hold it at the top. You're not going to have to, use the same amount of force as you use to spin it up to the top. But then you do have to impart some force. You can't just turn off the motor and have it stay there. You have to either lock it in place or do something else or keep applying current to the motor to hold it in place. And it sounds like for your application, to hold the same thing in place, there's just less current because the it's just like you said, maintaining the heat in the wire.
Right. And when we first approached it, because we were coming from a background where we were doing clutch control, which is sort of a cyclical thing, we ended up spending a lot of time figuring out ways to suspend this material in different types of cooling fluids. But then when we started approaching different applications for positioning, that's when we realized that fluid actually doesn't help us. So we then returned to air-filled and are now looking at different forms of insulation to really make this a green actuator for that subset of applications.
Okay. And then, so we were talking about we first started talking about like if you put current through it, it's going to contract. do you have as much control then on the other direction? Like, can you actually impart force then when you release, or is it only in that contracting direction?
We tend to think of it as a one way, like a unidirectional device, kind of like a solenoid.
Hmm.
We do use a bias spring, again, like many solenoids, to return it, and that so you can get some push in the opposite direction. But
Okay.
it's not the same amount as its forward direction.
So that actually would push the. So I'm thinking now of like a tall box that has a plunger hanging out of it by that 3 to 8 inches you talked about. You turn this thing on, the plunger can go all the way down. It can actually pull something down. But then if you release that power, then it's just going to pop up at whatever the spring that internally is.
Yeah, that's right.
So then you could have a stronger spring in there, but then it also takes more energy to overcome that spring force, right?
It's not so much energy as you're basically going to sacrifice how much you can lift or push, push or pull. So,
Okay.
that spring is basically cutting into the available power available to do the work that you're trying to do.
Okay. And like I said, I did reference this chart, but I didn't actually come back to it. The different force and displacement stuff. So it's kind of you're showing it kind of in the middle there, but what why are those other things kind of gapped? Why was there that gap that you're starting to fill with the kinetics product?
Uh, it was really just a kind of a discovery after we looked at what else is out there. Our for us the technology falls under this small displacement range, so something kind of akin to what a solenoid can do, but at a much higher degree of force. And there really is no other technology that falls into that space. So it's not that it was kind of a gap that people had missed. It's just that the science or the available tech that was out there couldn't really easily service that. So what we saw was a lot of different technologies were, trying to overreach a little bit or do things in, a variety of kind of fancy mechanical ways to enter that space. And by that, I mean the piezoelectric actuators start to look at inchers so that they could amplify how far they could go by taking small steps and like ratcheting its way in.
Uh-huh.
Whereas, let's say the electric ball screws, they started getting into very finely machined parts and very fine pitches, so they could get into super fine resolution. So these are sort of ways that other tech sort of is flying in to service the space. But looking at the strengths of the material, we think that there's lots of areas where this can outperform.
Yeah, that's great. Well, let's go back to the way you kind of came across this. We had obviously been introduced by former guest John Davis, and I had expected you to be like not I expected you, but I thought this was all going to be about material science and stuff like that. But you're basically a consultant who kind of came into the solution. So how did you actually? And I'm not saying you don't do material science, but how did you start to discover that this was a potential solution? And like, what was the process to get to the point where you're like, oh, not only is a solution for our job here, but also it might be a product.
Right. Yeah. And you're definitely not offending me by not calling me a material scientist. I'm definitely not by any stretch of the imagination. Really, how we got to kinetics and got on shape memory alloys was at By Performance. The real purpose of that company was to create transmission controls for motorcycles. So completely different field of work, completely different focus. And we had this overall system design in mind that would combine gear control and engine control and, more importantly for this topic, clutch control together to give a motorcyclist either push-button shifting or automatic shifting. And it was this
Right.
This clutch actuator that really stumped us for quite a long time. And what I mean by that is, a motorcycle a motorcycle clutch is a little bit like a automotive clutch on a manual car, where you have, in the case of a car, you're pushing a lever into the floor. On a motorcycle, you're pulling a lever into a handlebar. But really, that lever is acting either on a cable, or in the case of our our target bike, it's a hydraulic system. And in this case, it's like a master-slave arrangement where you're basically the master and you're pushing fluid down a pipe and it's pushing on a slave cylinder, which is mounted on the engine, which is working the clutch.
And it's still doing the same clutch action. Like I've seen animations of clutches before. It's basically just like disengaging the. Oh boy, I should say, Dean, I've gotten myself in so much trouble in the past where I started trying to talk mechanical stuff. I'm like, oh yeah, the camshaft, blah blah blah. Yeah, I don't know, but I've seen. Maybe I can find an animation of a clutch happening. Could you quickly explain what a wired clutch does?
Yeah, no problem. So, super simple clutch is not all that different from what you're going to find in vehicles. You imagine two discs that are pushed together. So they're kind of transferring torque, right? And what's pushing them together are usually just a bunch of springs. So in order to get a clutch to separate, in order to get it to slip or to separate, you basically have to overcome the force of those springs. And that's what you're doing with the hand or your foot, depending on whether you're riding a motorcycle or driving a standard car.
Okay. Yeah, that's pretty simple. That's good.
Oh yeah, deadly simple.
I'm just going to defer to all things mechanical for you,
So in our case, what's happening at the hand is you're basically controlling a master cylinder, which another word for that is like a piston pump. So you got a chamber and you got a piston and you're forcing that piston in, and there's something on the opposite end doing kind of the opposite effect. So like for every reaction there's a equal and opposite reaction. Down at the slave, it's basically pushing a rod that's separating those two discs in the engine. So what we found was, we needed something to push this piston, to more or less replicate this master cylinder. And, solenoids definitely couldn't do it for a variety of reasons. Too weak, and they had no positioning control. Like
the feedback component you're saying, right? Like it's usually like it goes, but you can't tell where it is.
Yeah, this idea of like a bang bang, like two position, definitely wouldn't work for us. Motorcyclists are very attached to their vehicles; they kind of feel everything that's happening. So you need a very high level of control, otherwise it's just not going to fly.
Right.
So
or you might fly off the bike. So there's that.
Also bad, yes. So piezos were definitely out, and that kind of led us to take a serious look at the motor-driven actuators, like the ball screw actuators, where you're taking a motor and turning that into something that's going in a straight line. And I always had a fundamental problem with that. It kind of drove me insane that we had to start with rotary in order to get linear. But I put those, I put those sort of gut feelings aside, and we really started to try to develop this piston pump using traditional actuators. But no matter how many different variations we tried, it always ended up too big and too bulky, and usually too expensive as well.
Yeah, because I imagine you have to do it pretty fast. Like, what were the constraints on the timing you had to get to?
Kind of in like big round numbers. A quarter second was kind of our max for how quickly we want to slip the clutch or disengage it. And then, we needed very fine control. So it's not that, we're bringing it to just one position. We needed that kind of response time across a range of different travels and pressures. And then it also would need to lock up as well at a pretty quick rate, so you didn't burn up your clutch. So what does that mean when someone says, "Oh, I burnt my clutch"? Well, if you let those plates slip too long at speeds that are, let's say, a little bit too high, you're really just burning up the material that's meant to be gripping itself. So you can really do some damage by letting a clutch slip too long.
So is that almost like two sanding plates, kind of like two sanding discs kind of going against each other? Is that kind of the idea, or what does that actually look like? It is a consumable, you're saying?
Yeah, it is a consumable. It's think of it as almost like one sanding disc working on one steel plate.
And then you just sand it for too long, and one's going to win, huh?
Well, yeah, you lose your sandpaper, and you have to toss that out and slap a new sheet on. And well, it's a little bit easier said and a little bit more expensive than just a hardware store grade sandpaper.
Right, right. Well, and you said you need to be really precisely controlled. Is that because you're going at different speeds and you're disengaging at different amounts of torque on it? Like what actually why does it have to be so precisely controlled?
Yeah, so great question. We set out to develop basically something that could control the torque from between the engine and the rear wheel of the motorcycle. So it wasn't that we were just trying to push plates apart. We were trying to develop a system that could control how much torque is getting delivered. And it wasn't just an on-off or a 0 and a 1. We really wanted fine control of just how much torque would go through. And that turned into a transfer function or an equation that relates, torque to the speed of the engine, to the amount of force or pressure we're applying on the clutch plates, and there's even a travel element to it as well. So it's a complex system, and we needed very fine graduation in order to tailor the gear shift, if you will, to the specific riding conditions. And there's just so many elements in play that we kind of needed a high resolution device as a result.
Is this is this something that you would have patented as like anti wheelie control, or what why did you decide to go on torque versus just like speed or other things?
Yeah, so the clutch is in essence a torque control device, and the same could be said, let's say, for like a brake disc on a car or on a motorcycle. It's a torque control device. In the case of the brake, you're trying to take energy out of the vehicle, and you're applying braking torque to slow things down. In the case of the clutch, it's usually locked, so you kind of want a 1-to-1. But in those special cases when it's slipping, you need to start getting into some different ratios of how much torque is going, and it's not always going from the engine to the rear wheel. Sometimes it's going the other way too, and it's these dynamics that can really upset the bike, upset the chassis, and upset the rider.
And just you're saying because of vibrations and just how it actually brings the force back into the system?
Well, you definitely want to be very smooth with the clutch control. Yeah, you don't want to send any torque spikes through it because, again, it comes back to rider safety.
So what did this ultimately... I mean, so this is a product that's still out there, right? I mean, you're still making the Shift FX, is that right?
Yeah, Shift FX has quite a few products in the aftermarket. But this product that uses the shape memory alloy specifically is really designed to cater to the factories that would install it as a factory option, because there's just such a number of aspects that we're touching on the bike that it's not really something that we can sell today as a bolt-on product.
Oh, you're saying because of the level of integration that you need to have, basically?
Yes, yeah, definitely. And particularly around not so much the clutch control as the engine control. Mostly for speed matching.
Yeah, how much? I mean, we've had people talking about ECUs on the show before, but in automobiles, so engine control units, or just really the processing in there. How much of that's happening in the motorcycle world these days?
In some cases, we're lagging. In other cases, we're leading.
Okay.
Like a modern motorcycle has a whole suite of typically CAN bus connected modules. So you could have an ECU, which is doing the fueling and the ignition. Well, it's talking to a fly-by-wire throttle device, which is controlling, the throttle or the amount of air that's going into the engine, which is talking to an ABS module, which is controlling the anti-lock brake system, which is talking to a suspension module, which is controlling active suspension. And
all this is fitting between someone's legs too. So there's also that. It's not like enveloping them.
Right,
which is crazy.
Right. So packaging is uber important. Luckily, these parts are small, and one of the more intriguing devices, which we kind of started dabbling in recently, was the inertial measurement unit, which I'd say in a lot of from a lot of aspects, the motorcycle industry is leading. So we're talking about a 6-axis. IMU is the acronym, or inertial measurement unit. It essentially gives these different CAN bus enabled devices an insight into exactly what the motorcycle is doing, how far it's leaned over, if it's going up or down a hill, how it's accelerating, if it's skidding, sliding, wheeling. Just a really amazing window. And with that kind of window, you can really improve how the bike responds to your inputs.
Really? Okay. I didn't realize there was that kind of. I mean, like, to be completely honest, my knowledge of bikes is very low, but I always thought that they were very much just a old school engine, with a chain going to a rear wheel. So yeah, I'll have to apologize about that. So I didn't realize there was this much level of control. And also, is this for like racing bikes, to street bikes, or what are we talking about here?
Right. So, all this tech that I'm talking about, you're going to find it on the high end sport bikes. You're going to find that on the high end touring bikes. But, just like electronic fuel injection, it trickles down even into, low entry commuter bikes, for example. So it's really just a matter of time. And this stuff will become more and more pervasive.
Still no airbags, though, huh?
Yeah, well, I think Honda tried to do that and actually has those things installed on their Honda Goldwing.
Really? That's the really, really big one, right? Like the cruising bike.
Yeah, it's a big bike, but maybe more interestingly, a lot of the suit designers. So we're talking like leather jackets. They're building basically the equivalent of an airbag into those jackets, and they have really interesting sensors, basically like IMUs, to tell them when the rider has a we call it a get off event, but it's a fall. And it triggers that airbag so that before you hit the ground, it's supporting collarbone, neck, those kind of areas.
Neck support.
Mm-hmm.
Right.
So you're basically strapping an airbag to you.
That's great. I mean, that's great. And I think that's kind of like a really good use of technology here. The interesting thing that we were talking about before the show too is that like the fact that this could be a completely a completely automatic, like just like an automatic car. So I could hop on a bike and potentially be able to not have to throttle, not have to use the clutch at all and shift at all. So it kind of makes bikes more accessible.
That's right. Yeah. Essentially, you get the convenience of a scooter with all the benefits of a motorcycle. So easy to learn, easy to operate, but it also can give you a progression path so that when you're ready to start experimenting with your shifting, you can flip it off of automatic and actually start picking your shift points. And that's sort of what we would like to see from any entry level rider. Our philosophy is not to take control away, but to give them a way to get on a motorcycle, but also get the most out of it. And for us, that means eventually trying it out yourself.
Right. Yeah, I think that's a really good point too, because you think about all the things you have to learn when you're getting on a motorcycle, and you have to learn how to shift while you're also balancing, you're also turning and signaling and all the other things. I'm sure from a safety perspective, that really helps a lot, actually.
Yeah, it can definitely help with rider concentration, and it really can help with balance too, because while the clutch is at the hand, the shifting's done at the foot. So you're constantly repositioning your body and changing your weight to do the shift, and that can be pretty unnerving for new riders, particularly those that have never driven anything but their parents' automatic car, which is becoming kind of a reality.
Count me in for that one, and driving less and less these days too. I mean, honestly, I think, and I've thought about like motorcycles in terms of efficiency. You can get high MPGs or whatever kilometers per. Whatever the non-imperial units
the SI
of
equivalent
efficiency is.
I'm with you. Yeah.
Yes. Yeah. But obviously there's just the enjoyment factor of it, but it seemed like really out of reach, to be honest.
Yeah, and I think what we'll see, hopefully, to get more people interested in it, it really is an exciting pursuit, either for commuters or just for enthusiasts. Is we're going to see more and more electronic bicycles, which are going to start putting motors between your legs, and those bikes are very easy to jump on. There's no real perceived fear factor. We're talking about sub-kilowatt motors, but I have a feeling it's going to be a gateway drug.
Oh yeah, I think so. I mean, I had a chance to ride an e-bike out in Seattle when I was out there, and those hills they're not easy, but they are a heck of a lot easier, and you can just zip around town, really. So it was really cool. how did you get into this in the first place? I mean, are you a rider? Like, why did you start going down the path of motorcycle design in the first place?
I can trace that back to about 2002, where I was involved in a university varsity challenge, like an inter-university competition called Formula SAE that
Oh
pits
yeah.
basically student-designed race cars against each other. But because of the rules of the competition, most teams ended up using a motorcycle engine. And back in our day, we were shifting that engine using really crude and rudimentary paddles and cables. And as a driver of that car, it made me, really irritated at how clunky it was. But as a student learning engineering, it gave me an opportunity to get involved in that car, turn it into, I guess you could kind of call it a thesis project, to turn that motorcycle engine into a Tiptronic or push button style race car, and that's exactly what I did. And after graduation, I realized that there wasn't a lot of products or features like that in the motorcycle market, so it kind of led me into that line of work.
And I mean, when you have all this stuff too, I mean, it seems like there's always kind of this underlying level of control there as well. So like, what does that actually look like when you're designing a new product? And I guess this is just more broadly for your consulting company too. Um, what are you actually doing under the hood in terms of control? Like, what kind of micros are you doing? Are you doing Linux? Are you doing bare metal? Are you doing RTOS? What are you actually putting inside the controllers?
Right. So we are starting from bare metal. We have developed our own distributed operating system that can work, either on the same circuit board between chips that monitor each other, or can communicate to a third-party device that is within our suite of products. So it was a ground-up effort to develop our operating system.
I mean, why did you decide to do your own versus doing an off-the-shelf RTOS or similar?
That's a great question. Maybe easy answer is stubbornness. But
a common answer too, yeah.
I can't tell you. I mean, outside of the context of this question, how many times we've tried to incorporate third-party software or firmware solutions on a whole variety of applications, and for some reason we always end up in a trap where we're spending more time training and learning and then realizing deficiencies.
Right. Rewriting their code. Yeah.
Well, usually these things are locked or prohibited from touching to maintain warranty or what have you for the license. And it's when you hit these barriers or you identify, things that you can't do but could do if you had your own foundational OS that just keep reinforcing this need for ground up development.
Right. The best part is you get to write your own drivers. The worst part is you have to write your own drivers.
Yes, it's true. Yeah. The interfaces is probably the worst part of the job.
But it also sounds like, I mean, like if you've stuck with it, I mean, I think it'd be problematic if you're like every year you're like, all right, we're starting over again. But if you're, maintaining it and you're developing as a, IP effectively for years and years and years, then that can be really valuable, because then the next time you start a project too, you also have this knowledge base that you've created that's also proprietary that you can use over and over again.
Yeah, it is a good fallback, and I mean, perhaps the most rewarding aspect of it is if I can relate it back to the motorcycle and the electronic shift transmission is, we are constantly riding and testing. When we find that there's an aspect or a behavior that we're not completely happy with, we can go in and actually, go straight to the heart root of the problem. And it could be quite abstract or complex, but, with that sort of broad understanding of the whole system, it makes a change happen quite rapidly so that we can go back out and validate or, test internally, validate, and then go to the street testing. But I don't think it would be too easy to do that if, we didn't have, a very deep level understanding of how it's all put together.
And so, like, what is the relative power of like processing that's on board? Is it like M0 level, M4s? Is it like a, higher level, like a Linux like an IMX 6 or 7? What kind of levels are we talking about here?
Yeah, it's we're able to do most of the functionality with just 8 and 16-bit processors, so even below M4. But I see us transferring to 32-bit, potentially floating point math, because we have a variety of physics engines that are constantly running and updating inside that chip, and we see a path where we need to develop even more advanced physics engines that are need to execute in real time. So I see us going there eventually.
Yeah, well, and then you get more access to better peripherals, stuff like that. You get the CAN buses, you get the LIN buses, whatever else is thrown in with the everything in the kitchen sink that they throw into chips these days. But it's always a painful switch over, I'm sure.
Yeah, definitely. It probably will depend on the level, like the level of target bike and the price points before we make the jump. It'd have to be a pretty premium product. We can do a lot with the 8 and 16-bit systems, but to really push the state of the art, we are. When we talk about running physics engines, we're essentially predicting what engines will do, what clutches will do, what bike chassis will do. So the math can get quite complex, especially as you start to throw in the feedback from the IMU and now are becoming sort of aware of the whole state of the motorcycle, all the forces, all the accelerations that are acting on it.
And so, like, what is it like? Could you explain a little more? Like, so if the bike's on its, say it's in a bank and it's like turning on its side, or it's leaning to one side, will that actually change the nature of the motor, or is it just like a big state machine that's internal to it? Like, how does that actually end up impacting the control of the engine?
Right. So the engine power is not too affected by the lean angle, but certainly the traction. Or let's say available traction on the tires goes down as a result. And the reason why is because some of the available grip is going towards keeping the bike from sliding, because it's got to react to that centrifugal action from the turn itself. So, that's where torque spikes, because of, events on the motorcycle, have to be carefully managed so that you never, breaking grip in a way that might cause an issue.
Oh, I see. Okay. So you might even, just to keep going with this example, right? So if the bike is leaning and you're saying, okay, we definitely can't have a torque spike, then that's an input then to your clutch program, because you can't bear as much slippage or whatever happens internal to the clutch then.
Right. So it might create like an inhibit event that might, feed into, we do use state machines quite heavily. So that kind of information can be used to change sequences or inhibit certain actions.
Right. You have to be clear of some flag in order to actually engage an actual shift event or whatever the actual state machine is. That makes sense.
Yeah. I mean, it's not just used by potentially us for ABS systems. Lean angle is also critically important, because if somebody's, reefing on the brakes because they're in a turn and they don't like where they're heading, that module has to be very careful on how it controls the braking, because if it may decide not to touch the brakes at all, and that can cause a problem, right? It's going to push the rider too far forward. Yeah. But if it locks,
that's a real problem.
The alternative though is it locks, and then the bike, you go straight down to the ground at that point. So it's that happy medium, which is so critically important, but challenging to obtain.
And so, and you're mentioning like third-party modules, or just generally modules outside of one thing. So this is all talking over a CAN bus, but is there like standardized messaging? Like, how do you know that you're this shifting unit and there's also an ABS unit? Do you have to talk the same language, or like is there like standard headers that you send to one another? How do you actually standardize that communication?
It tends to follow the CAN bus protocols. So every message will carry an ID which identifies it, and then that message might matter to some modules and it might not to others. So it's really up to that node to say, yeah, I'm interested in that information, and take the message in, process it, And if there's an expectation for a reply, then that can go out or not.
So some of the protocols you're talking about, though, like again, you have to excuse my ignorance here. The CAN bus protocol is actually saying like it's like a published mechanism for the braking system in general. Like, hey, I'm a braking system. I'm about to fire or something like that. Is that kind of how it works?
Yeah, I would say it's not standardized. No, so it has to be kind of established when, by the people who are designing that CAN bus network. These are the IDs. We're going to do, let's say, this style of messaging. It's going to go out on a fixed like beat pulse or frequency, or this is going to be event driven messaging. It's flexible essentially, so it's not really stipulated. It could be stipulated by a manufacturer or a higher organization, but it's not. It's not that our TCU is message ID 99 and it always will be 99 and it'll always
right.
Transmit.
There's no lookup table to see the RX whatever or ShiftFX version of something, right?
That's right.
So then, if the ShiftFX wants to work with different things, you have to have programmed in which ones it works with. Is that kind of the idea?
Yeah, and that again kind of goes to why we're approaching the factories. Is you can't just drop in a CAN bus module into the bus and expect everything to work. It's these devices have to be set up to either provide the information we need or we need to send the information they need in order for these features and functions to actually be working and useful for the rider.
Yeah, I mean, yeah. Otherwise, you're basically sending mail to something without the right address, right? You're just sending mail to the central location. You're like, yeah, well, hope it gets there.
Yeah, just a bunch of spam.
Right.
On the flip side, though, there are third-party tools that can listen to the network, and that can, that can give you diagnostic information. So those can be quite useful as well.
Right. We've had Earl on from Machina before, and they do an open source CAN bus protocol analyzer thingy. That's where I think I remember hearing some of this stuff, but it's amazing to me that there's still no it still seems not abstract enough, but there's not much cooperation between the companies. Then that's what's amazing to me. It's like you have to talk the specific language of each module or whoever's it is. The assumption that you're always working with the same company's equipment or you can talk to it.
Yeah, I think you make a really good point there. It seems to be like barriers are thrown up for the sake of just putting barriers in place, and they're not always driven by the right mindset, in my opinion.
Yeah, the motivation is money, like usual, but that is a consistent thing in our world, regardless of profession. It seems like. Speaking of money, you guys also do other consulting stuff, and that's kind of how it seems like you got into this. What else does? Sorry, I keep forgetting the name of it's by
Performance.
By Performance. Yeah. Byperformance.ca. That's your website. What else do you guys kind of focus on? Is it mostly in the automotive motorcycle realm, or is it outside of that as well?
Our products division, whether it's robotics or motorcycle products, are, I'd say, pretty far removed from our consulting work. We take more of a regional focus to our consulting work, and in my home province of British Columbia, that tends to lead us down the road where we're working with power generation, forestry, marine industries here. So we've worked on a whole variety of kind of interesting projects. So over the years, I've developed kind of a side set of expertise around power generation from biomass, which is a fancy word for wood waste.
I was going to say burning trash, yeah, but making it into electricity, which is actually really cool. And that's isn't that the one where wasn't that Sweden or Finland ran out of trash? I remember some Nordic country they're like, yeah, we're out of trash now. We need things to burn so that we can make electricity. It's like, oh, nice problem to have. Too bad shipping's so expensive.
Yeah, well, in British Columbia, our forestry industry is a huge part of our economy, and it generates a lot of wood waste. So that for us, it's not a municipal trash stream where you've got all kinds of contaminants in it. It's actually a pretty clean stream. It's really just a question of how wet it is when it comes to us.
Interesting. So then is that literally just using sawdust to boil water kind of thing, and then make steam, or what does a biomass plant look like?
A lot of forestry facilities, particularly like pulp and paper plants, will have things called power boilers, which take wood and burn it. And the ways that it burns that wood are pretty varied. You can have something as simple as a pinhole grate. So you're just throwing wood on a plate that has air coming underneath it, and you get a big fireball, and that's used to generate steam. Boil off water inside tubes.
Yep.
But you also have kind of really interesting and unique ways of burning wood. One of the projects I recently worked on used something called a fluidized bed, which was a giant industrial sandbox that was aerated from underneath with a 1,200 horsepower fan, so that the whole sandbox would lift up, and you drive wood into it and you light it off, and that thing essentially becomes like Dante's Inferno, just a giant swimming pool of fire. Yeah, pretty amazing.
Giant swimming pool. I like this. Yeah, yeah. And it sounds like because of the air injection too. It's kind of like when you superheat a kiln, or not a kiln, but a forge, right? Don't you have to usually inject air to superheat like coal or coke to do like smelting?
Yeah, definitely similar to that. So the reason why they use sand in this case is it actually envelops the solid wood as it gets introduced into the boiler through some kind of a feed mechanism, and it helps burn wet wood, which is typically what you're getting. So it'll quickly, evaporate that water and then start breaking down that wood into its, molecular or atomic constituents, and then that's when you can start generating combustion and getting heat back from that fuel.
And this is for like localized generation at a plant, or is this more broadly for like powering homes in the area?
It's a bit of a mix. If it's a pulp and paper plant itself, it tends to have a massive power demand, so it'll consume its power. Whereas this last project with the fluidized bed, it was a standalone power plant. So wood came to the plant, and it exported its power to keep the lights on in the houses in the area.
Well, that's cool. Yeah, that's really cool. What are some of the other constraints in that system? Like, is that like, or like, what are the parts that you're actually designing in this setup?
Kind of one of the more interesting aspects for me, as from a control engineering point of view, was I had a heat and mass balance for this plant, and it had, I want to say, about 100 different nodes. So you've got this open loop cycle on the combustion side, where air is coming in, fuel's coming in, and then you have everything coming out the stack, like CO2 and nitrogen, etc. Lots of H2O, because you're basically just steaming that off the fuel.
Right.
But that whole process, which includes lots of thermal equations to figure out what kind of energy you're going to get out of it, has to intertwine with this closed loop water system, which is very, very complicated. And it's amazing how many different times you need to take water at one state or steam at one state away and reintroduce it here and pull it out there. And, really at the end of the day, though, we're just passing it through a turbine, and it's going back to the boiler and back and forth and back and forth. But
right.
the details are amazingly complex, and the kind of control equipment you need to modulate all these things.
Right. Well, I mean, you don't just open a steam valve with your hand or something. You want to use machines, and there's a lot of pressure and temperature, like you're saying, and pretty crazy.
Right. And we try to cut out the manual control as much as possible, so that somebody in an operating room can sit back and have all those levers and handles more or less at the click of a button. And
yes,
what was quite cool on that project is, and I will take no credit for it, but we put the whole control plant on a tablet that an operator could then take anywhere in the plant. So you essentially can have a control room with 20 screens fit on a tablet, and you can sit anywhere you want and control it, and actually see the events happening right in front of your eyes.
That's pretty cool. But usually that also means that, isn't that also like SCADA systems that are then like opening themselves up to like open ports in the internet kind of thing, where like there's municipal water stations that are like just open with like no password kind of thing.
This was a whole closed. I'm not sure if
Okay.
intranet's the
All
right word.
closed system.
Yeah, closed system.
Yeah. Yeah.
Sorry, no
Good,
backdoors
good.
that I'm going to reveal in this call.
No, that's good. That's what I mean. Like honestly, that's what I want. And it's like I feel like the modernization. Like some of them, it sounds like that's actually a really useful thing. The tablet, like you're talking about, to have that you're on site. You're like, all right, now I'm going to actuate this valve, and I'm standing in front of it, and I see that it turned red, and the light turned on, and I can hear it going. Like that's actually really valuable instead of radioing between yourself and the control room or whatever. So that's pretty cool. But I feel like in the same stroke, they're also selling like, and you can do that from your home. It's like, well, maybe you don't need to do that,
Yeah, I kind of like the philosophy of closed intranet around the plant, and particularly all the controls with, let's say, a one-way firewall that allows telemetry out, because there are decision makers that aren't in the plant that need that information. But the idea of a manager remotely shutting a valve is terrifying.
Yeah, I agree. Yeah, and I mean, like, and this sounds like it's big stuff. I mean, like, what kind of levels of power generation are we talking about here, too?
So that last power plant was 36 megawatts, and
wow,
I want to say it was burning. Let me see, about 60,000 pounds an hour of wood waste.
Wow. And so wood waste is like coming off, like, is this like branches that are trimmed off, things that are getting turned into planks, or like what is wood waste, or is it like the pulp, like you're talking about, like the offshoot from the pulp plant, or?
So it was mostly sawmill residuals. So, the trees are coming in with bark and branches, sometimes with tops. There's a lot of slash that's still left in the bush, but sometimes because it now has value as a fuel that can be drug in by truck. And then the sawmilling produces quite a lot of sawdust itself, and you get then rough cut lumber that has to get planed into finished lumber. So that planing creates a lot of chips, and then you've got a lot of kind of odds and sods that don't meet grade that kind of end up in this pile. And depending on where you're situated, all that stuff has value. So these plants are the power plants. Plants fight with other plants like pulp and paper that can actually turn that fiber into paper, or they're fighting with. There's quite a few plants in British Columbia and Canada and the U.S. at large that produce pellets that tend to get exported.
Oh, yeah.
So that fuel is, even though it may be just adjacent to the plant, there's somebody who's willing to take it, dry it, pelletize it, and ship it to Europe for use in their biomass systems.
Yeah, that's like carbon economy that's coming from above the ground instead of below the ground, right? It's pretty crazy.
It is renewable power. Yeah, it's a carbon economy. It's renewable. It's green. I think there's ways to make it greener.
Well, it sounds like if you're, I mean, like you're literally using 100% of the tree too. It sounds like, so that's amazing. But that's really cool. That's really cool that happens.
Yeah, and compared 20, 30 years ago, we had quite a few things called beehive burners in this province where the wood was a problem. It truly was waste. So they would just pile burn in giant things that looked like beehives. And they just had a conveyor belt throwing it on the pile. And really the beehive was just a screen to keep the sparks from starting forest fires. No emissions control, Nothing like that.
Wow. Yeah. Well, that's great. That's great that it's changing too.
Definitely.
What is this? So what is? You also sent me a video. I've been looking at it, like trying to figure out what I'm looking at here. This is the screen cleaner. Is this the same thing? Is this for this power plant project or something else?
So you are looking at a different project, but it is a power plant unto itself. So that was a project we did for a different company. They call it the Coanda Screen Cleaner. I affectionately refer to it as the dam brush. And really what this is it's like a micro hydro plant. So rather than creating a big dam and forcing the water to go down a pipe to spin a turbine that's at the bottom of the dam. This is called run of river. So what you're looking at is an intake screen for water, and that water is then sent down a big pipe called a penstock way down the riverbed, and then it goes through a turbine down there, which generates electricity and then spits it out at the bottom of that river. Because it's operating in nature, that screen gets dirty. So essentially, we need to run a giant toothbrush back and forth over it to keep it clean.
It's a damn brush, huh?
It's a damn brush.
That's great. That's great. And like what would actually get caught? There was just like branches and some other things like that would actually like jam it up.
Usually, it's like the little bits of leaves that accumulate at various times a year. Like a lot of this stuff will just flow over, but there's just certain geometries that just like to hang around. So brushing off little particles of leaf can make a big impact on how much power you can pull out of the hydro plant.
Huh. And what's the relative power of that kind of hydro plant?
That one I think is also producing like 40 megawatts, which puts it at the high end of the range for run of river. So run of river is at a totally different scale than a typical hydroelectric project, which would be talking like gigawatts of power. Right. But it also has a much.
I grew up near Niagara Falls, so I've seen some of the big ones.
Yeah, right. So at least with this one, it's got a much smaller footprint, so you can put it in remote locations, and it's you don't necessarily take all the water out of the river, so you can actually maintain sometimes the river ecosystem.
Right.
Without
for like fish getting back upstream, that kind of thing.
That's right. Yeah.
That's really great. So, and then but it seems like in both these cases, what are some of the constraints around designing so this one's an outdoor system, and then obviously the setting up something that has a large fire breathing thing, what are the reliability constraints that you're dealing with?
The one in the Run of River project is interesting because they're very remote. We can't bring the river to the maintenance yard, and it's usually way out there in the mountains. So things need to be able to run autonomously, and they need to be very reliable. Not to say that the power plant in a case is not reliable. In fact, it has its own weird set of criteria in that plant has to run uninterrupted for 50 weeks a year. So when it starts, you really want it to run. No joke, 24 hours a day, 7 days a week. You do not want it to turn off until it's scheduled maintenance cycle. So I can't tell you how many different ways that plant can turn off. So
can turn off, you're saying?
Can turn
just
off,
because of safety mechanism?
Yeah. Various trips in the system will, by design, take it down in as safe a way as possible. But that has, can have very tough consequences on equipment because it can be very hard on the equipment itself, but it's also very time consuming to take a plant down and bring it back up.
Right. I just think about the heat cycling of, if you have something that's roaring like the fires of hell, like you were talking about, and then it drops really quick. I'm sure that there's some thermal events that happen. And then also you have to heat it back up. You got to make sure everything's in place when you turn it all back on.
Right. Yeah. So that fluidized bed, the big sandbox, it cools down rapidly. And if it gets too cool, you can't just throw fuel on it. It won't burn. So you have this sort of window of time for that system. The turbine is in some ways even more sensitive because it's, locked into the grid at 60 hertz. When it trips, it immediately has to open the breaker and disconnect from the grid. And that's a big hit of generation that drops out for, typically smaller remote communities. So, going back to that whole kind of telemetry case where you got to get the information out of the plant, that information becomes very important to try to provide some clues and hints to the maintenance crew as to what needs to get looked at, before it becomes a major issue.
Yep. That's That's a bad call to get at 2 a.m. Is that the it's bad if you get a call at the 2 a.m. It's even worse if you didn't have a here's what it probably is, kind of message going with it, either from inside the plant or whatever. So,
well, the emphasis is, I'd say really on predictive maintenance as opposed to like firefighting, where there's now something's gone very wrong and you have to pick up the pieces. And, you hear a lot of talk about, AI, artificial intelligence, machine learning, big data. I don't see a lot of people talking about, real use cases, but these power plants and these large industrial facilities are great examples of big data. You have, 500, 1,000 sometimes of nodes, that are kind of IoT or at least sending out data that's being recorded. And so you're accumulating all this information. But the analytics that you need to run to do this pattern recognition are extremely tedious and time consuming. So, I see opportunities down the road for people to get into that line of work for predictive maintenance using big data and AI.
And so this is like a distributed control system you're talking about, right? Like having a range of sensors, that kind of thing?
Yes, distributed control system. Well, that's an interesting question. Usually it's consolidated inside of a single plant control system, but you have all these distributed devices that are in the field. We try in this case, and I understand why, we try to restrict the number of distributed control systems. You do want kind of redundancy or backup of your main control system, but try to keep it all in one room or one building.
That's cool. Yeah, and you're totally right though about the generating of that much data. It's just you could look at it, but if you always just said when this sensor goes below 3, then we got to turn the machine off. That's almost as expensive as just having every third month we turn it off or whatever it is. Like it's better if you can hold out until the known point of, okay, well, in the past 40 times we ran this machine, when it got to this operating point, that's when the optimal maintenance was, and we're definitely going to do it then. You can start to optimize for that then, and decide to take the machine down as needed, so that you're not breaking anything.
Right, and I'd like to think that an AI bot or a program can start to do that for us, because it's a lot to ask individuals in the plant to do that. There's so many different aspects. So nobody can review 2,000 data points over 5 years to figure out certain very subtle patterns that actually can lead to breakdowns or bad events.
Right. And expensive events too. Yeah,
definitely.
Well, Dean, we have gotten through quite a lot of. We've gone from linear actuators to biomass generators. So there's a long distance in there, and that's pretty cool. You're doing some very cool stuff. You had mentioned though that you are actually looking to hire someone as well.
Trying to find an embedded systems guru that can come into our team and work with us as we develop a next generation of transmission controllers for the motorcycle industry. So, looking for a talented individual who, has an interest in, actually applying, their skills to some real practical problems. And, that's essentially it. If anyone's interested, send a resume to hr@byperformance.ca, and we will definitely take a look at it.
Yeah, that's awesome. And you said remote might be okay for the right person too. I think that's always important to say if that's
for sure. We're looking. We're happy to do a broad net reach. We're looking for talent.
Yeah, that's really great. I mean, the things you talked about so far too. You're doing some very, very interesting things. So I'm sure there's someone out there looking to put some processors onto bikes, and then maybe once in a while you got to go out and test them. I don't know. Maybe you got to go ride around for a little while.
I won't say you have to come with a motorcycle license, but it would help.
All right, that's cool. Where can people find out more information about you and the companies, and where they might be able to see all this stuff we've talked about today? Obviously, we'll have show notes, but if they want to go directly to the websites.
People want to look at the motorcycle products and the transmission tech, go to shiftfx.ca, so shiftfx.com, and then that's important. And then the linear actuator tech can be found at Kinetics Automation. And Kinetics is spelled KINITICS, automation.com.
Great. Yeah, and byperformance.ca is the one you mentioned before too. So that's good. I'm sure you're going to get some interesting people applying there. Well, Dean, thanks so much for talking here today. I really appreciate it. And I look forward to hearing about the next thing that you're putting together.
Definitely. Thanks for having me on the show, Chris. I appreciate it.
All right. We'll talk to you soon.
Sounds good.